The next rule we're going to look at is the chain rule, which allows us to take derivatives of function compositions. So when we have a function composed with one or more functions, in order to take the derivative, we need the chain rule. So the chain rule says if g is a differentiable function at x, and f is a differentiable function at g of x, then the composite function f of g, or f of g of x, is differentiable at x, and we can find that derivative by using the product of the derivative of the outside function with the inside function remaining intact, multiplied by the derivative of the inside function. Right? So if you look at it, so here are a few things that are necessary for the chain rule to work. I must have g be differentiable at x, because we are going to take a derivative of g at x, and we need f to be differentiable at g of x, because f is differentiated at g of x. So when we take the derivative of this composite function, so our function is f of g of x, we first take a derivative of the outside function, the f prime of, and the inside function remains the same initially. So f prime of g of x. We don't take a derivative of g at that point, but then we multiply the result by the derivative of g. Okay, so if we go back and use the Leibniz notation, and we define y to be f of a function u, and u be a function of x as g of x, as long as they're both differentiable, then we have the ratio of dy dx is equal to dy over du times du over dx. So let's look at some examples. The first example, we have a basic function y equals sine of x to the fourth. So again, it's a composite of sine of x and x to the fourth. So if we look at them in terms of the notation we had, we can define y to be sine of u and u be x to the fourth. And following the chain rule that we saw, the first thing we're going to take is take the derivative of sine and leave the x to the fourth alone. So derivative of sine of u would be cosine of u, and u is x to the fourth. So we get cosine of x to the fourth, and then that gets multiplied by the derivative of the inside function, or derivative of x to the fourth, and that would be 4x cubed. And last thing we're going to do is just kind of clean this up and rewrite it in a nicer format. 4x cubed cosine of x to the fourth. Okay, so next we'll look at this slightly different looking function, sine to the fourth of x. Right, so notice in this case the 4 is the exponent on the sine, not on the x. So recall that saying sine to the fourth of x is the same as saying sine of x quantity to the fourth power. So again, I do have a composite function in here that I need to take a derivative of. Our outside function in this case is u to the fourth. Something's taken to the fourth power. The inside function is sine of x. Following the chain rule, again, we first take a derivative of sine of x to the fourth, or u to the fourth. And that would be 4u to the third, or 4 sine of x to the third. And then we go back and multiply by the derivative of the inside and multiply it by what we have. And the derivative of the inside function, which was sine of x, is cosine of x. So as a result, again, just to clean this up and bring it back to the way the notation had started, 4 sine cubed of x cosine of x. Okay, let's look at one more example here. I want to find the derivative of y equals quantity 5x plus 3 over 2x minus 7, the whole thing to the 9th power. So again, a composite function, we have what's inside of that parentheses is a function, and that function is taken to the 9th power. So it's composed with the function x to the 9th or u to the 9th, whatever variable you want to choose. So if I look at it as y being u to the 9th and u being 5x plus 3 over 2x minus 7, we go ahead and take the derivative of u to the 9th, which would be 9u to the 8th, and make sure the u stays u, so 9 times 5x plus 3 over 2x minus 7 quantity to the 8th power, and multiply that by the derivative of the function inside the derivative of u, and that requires me to use the quotient rule, and the quotient rule says I got to take the derivative of the top, which is 5, multiplied by the denominator, 2x minus 7, minus the derivative of the denominator, which is 2, multiplied by the numerator, 5x plus 7, over the denominator squared. Okay, so at this point the derivative is completed. We just need to algebraically simplify this a little bit. We'll start with distributing what's on the top. So I have 10x minus 35 minus 10x minus 6. That's distributing the 5 and a negative 2 into the parentheses. Here I can combine the 10x and a negative 10x. They cancel. Negative 35 and negative 6 give me negative 41. And then I can multiply that times the 9 and kind of rewrite this parentheses as a 5x plus 3 to the 8. So that goes on the top. So on the top I have 9 times the negative 41 times the 5x plus 3 to the 8. On the bottom, I'm going to have a 2x minus 7 to the 8 from the first parentheses, and the 2x minus 7 to the second from the second parentheses. Those combine into 2x minus 7 to the 10th power. So my final answer is the 2x minus 7 to the 10th power on the bottom. Once again, that's the 2x minus 7 to the 8 and 2x minus 7 squared combined. And in the numerator, we have the 5x plus 3 to the 8 that was left over from here, and 9 times negative 41, and that gives me negative 369. And that's as simplified as we can get this to be. Right? So our next example helps us establish a new derivative rule. So we'll start with trying to take a derivative of y equals 5 to the x power. Now recall, we already know how to take a derivative of e to the x power, but we haven't taken a derivative of any other constant to an exponent, a variable exponent. So what we gonna have to do is rewrite this. So if you recall, if I take e to the natural log of b, that's equal to b, right? E and natural log are inverse functions. So if e composed with natural log of b gives me b. So that means if I have b to the x power, so if I take this to the x power, on the other side, I would have e to the natural log of b times x. Okay, so that lets me rewrite 5 to the x, right? So that means 5 to the x can be rewritten as e to the natural log of 5 times x. Right? And then I can look at this as a composite function of e to a power, and that power itself is a function of natural log of 5 times x. So we look at y be e to the u, right? So I have e to this whole power, and my u is natural log of 5 times x. And again, just remember, natural log of 5 is just a constant. I can punch in a calculator, get a decimal value for it. It's just going to make it look uglier. So if we're just going to leave it as natural log of 5, remembering that it's a constant. So now, as I'm taking the derivative of this function, the e to the u, when I take a derivative of, remains e to the u, or e to the natural log of 5 times x. And then I need to take a derivative of natural log of 5 times x. Again, since it's a constant times x, just like 7x, the derivative would have been 7. Derivative of natural log of 5 times x is just natural log of 5. And last thing we do is rewrite this e to the natural log of 5 times x back as 5 to the x in the form we started with. So the derivative of 5 to the x is 5 to the x natural log of 5, right? And again, if we check that with our derivative of e to the x would have been e to the x natural log of e, and natural log of e is 1, so it would just remain e to the x. So that kind of allows us to expand on our exponential functions that we can take a derivative of and come up with a general formula. The derivative of any constant to the x power is this constant to the x power multiplied by the natural log of that constant. Right, so next we're going to look at longer chains. And as we look at this, the reason why we call this rule the chain rule should become a little more clear, because as we create these more complicated functions, we're going to get a chain of derivatives that I need to consider. So in this case, I have 3 functions. Y is f of u is g of x, and x is h of t. Right, so I have the function h of t plugged in here, and then that function is u, and then u is plugged into f. So I have f of g of h. I'm sorry, f of g of h. Right, so as long as they're all differentiable, then we can just take the derivative with respect to t by using the chain rule twice. So dy over dt would be dy over du. So that's the derivative of the first function with respect to u, multiplied by du over dx, the derivative of the first inside function with respect to x, multiplied by the derivative of the last function that was plugged in, dx over dt. Okay, so we'll look at one last example of this longer chain rule. So we want to take the derivative for sine to the 5th of x to the 8th. Right, so here I have 3 functions composed. X to the 8th is the innermost function. Then I'm taking the sine of that, and then the whole thing is taken to the 5th power. So if I rewrite this in that order, I have x to the 8th inside of a sine, and then that's inside of the power of 5. So this will give me the chain of y being u to the 5th, u being sine of w, if I make up a function, and w being x to the 8. So taking the derivative, we're going to start with u to the 5th. Derivative of u to the 5th would be 5u to the 4th. And then all the inside parts will remain the same. So it will be 5 sine of x to the 8th to the 4th. Then we're going to multiply that by the derivative of the second function, which is sine of w. And that would be cosine of w, with w being x to the 8th. So I get cosine of x to the 8th. And finally, we get to take a derivative of x to the 8th. And derivative of x to the 8th is 8x to the 7th. Right, so these are all multiplied together. And last thing we do, again, in this case, is clean it up. I can put 5 times 8x to the 7th in front. That's 40x to the 7th. Rewrite our sine of x to the 8th quantity to the 4th as sine to the 4th of x to the 8th. And cosine of x to the 8th remains cosine of x to the 8th.